The Pacific Northwest is a location well renowned for its majestical landscapes, beautiful greenery, and abundant wildlife. However, as humans constantly expand and the interface between humans and nature grows, this natural beauty, specifically the wildlife, are put at risk from the hazards posed of crossing roadways. In response to the increase in wildlife vehicle collisions, wildlife overcrossings have begun to be built to allow for the safe passage of animals crossing roadways. In the state of Washington, the success of this type of structure has been displayed through the building of the Coachella Lake Wildlife Overcrossing that spans I-90. Based on this success, the Washington Department of Transportation is looking to implement these wildlife crossings in more locations along Interstate 90. The following discussion details the way that the topographical site constraints, aesthetics, structural efficiency, and cost were designed for one of these additional wildlife overcrossings.
Before we get started presenting our design, allow me to introduce part of the Oregon Institute of Technology 2022 Student Steel Bridge Competition team. I'm Caroline Herkamp, and I'm the team captain.
I'm Serena Moha, and I'm a part of the construction team.
I'm Hannah Bruno, and I'm a part of the construction team.
And we're pleased to present our design to you today. As with many projects, the design of this bridge was primarily governed by site constraints, which included a defined bridge envelope, skewed footings, and a cantilevered end. Other key factors in the design included a maximum size of members that could be installed, as well as no mechanical connections being used. With these constraints, a deck truss bridge type was selected. Using the software RISA 3D, a variety of truss configurations were examined, and the eventual design of a truss piece with a single connection in the middle was decided upon to limit the number of connections that would need to be made during the construction process. This was desirable to minimize construction time and therefore also minimize cost. The design of 4 lattice pieces on the top of the truss and 2 pieces on the bottom was selected for both structural and aesthetic reasons. From a structural perspective, because the bottom section of the stringer is primarily subjected to tension, removing 2 of the lattice pieces was an effective way to reduce members and the overall weight of the structure. Aesthetically, this truss design also mimics the setting sun seen on the West Coast. On the cantilever section, the truss configuration remained similar to keep with the aesthetic value of the rest of the bridge, but a tapered end was also selected to reduce weight and add visual appeal.
The analysis conducted on the selected truss design was also completed using the software RISA 3D. With the previously discussed truss design selected, loads were applied to the bridge for each potential load case. Analysis for the bridge was then performed on the bridge by using a solver function integrated within the software package. Second order effects for the bridge were solved for by allowing p-delta analysis to be performed. Different hollow structural steel sections were checked in the model by using the section set list, which allowed for different groups of members to be changed quickly during the analysis process. Using the code checks within the software, different member sizes were selected to meet strength demands. Another useful part of RISA analysis software is the ability to analyze both vertical and lateral deflections. By using an envelope analysis procedure for all load cases, node deflections were checked for every possible loading, which allowed for analysis to verify that vertical and lateral deflection maximums were not being exceeded.
When it came time to fabricate the design, most of the work was done using grinders to achieve the steep angles seen in the truss members. Fabrication time was minimized by training each member of the team on how to work all the necessary machines so that no matter the task that needed to be completed, it could be completed by whoever had the time. This built in redundancy into the fabrication team as there were no tasks that were only able to be completed by one person. Regarding the actual fabrication of the pieces, time needed was minimized by creating jigs and batch fabricating pieces that were all the same. All pieces were also continually fit checked with their adjoining members to ensure easy construction assembly. In addition to continually fit checking the fabricated pieces, the process of easy construction was also aided by considering constructability throughout the design process. One of the primary ways that the final design reflected this consideration was through the selection of a single mid-section connection being used for each truss section. Individual connection points were further minimized by having the perpendicular lateral bracing connect at the same connection points where the trusses met. An important aspect of staging was ensuring the correct pieces were assembled and ordered during the construction. This was done by using tape at the end of each member using colored tape for easy member identification. This allowed for staging the members in sequence through color coordination.
Thank you for taking the time to hear our unique approach for the wildlife overcrossing over I-90 in Washington State. We appreciate your consideration and look forward to the opportunity to assist you further with the next stages of the design process for this bridge.